Today we are going to discuss the design of transformer core. First of all, let's see what are the design steps for the design of transformer core. The first step is to find the net iron area of core, that is AI. In most of the cases, it is calculated with the help of the equation for EMF per turn, that is ET. ET is equal to 4.44 FBM From that equation, we will find the value of AI, net iron area. Then we will assume a suitable value for stacking factor, that is Ki. So by knowing the value of Ai and Ki, we can calculate the gross iron area AGI. That is AGI is equal to Ai by Ki. So once we have obtained the value of AGI, then we have to decide the suitable cross section. That is whether it is a square core, a stepped core, or the number of steps can be selected. At this stage, we have to select the type of cross section to be used for the transformer core. Then the main thing to be noted is that the corners of the core should touch the circumscribing circle. And in most of the cases, we will prefer circular coils. This is due to its superior mechanical characteristics. But in the case of a shell type transformer, we have to use a rectangular kind of core. Next, let's see what are the different types of core constructions that can be used for transformers. First one is a rectangular core. This is used for shell type transformers. Next is square core. In the figure, we can see the cross-sectional view of a square core in which all the sides are equal to small letter a. And the circle, this is the circumscribing circle. The circumscribing circle touches the four corners of the square core. So small letter d is the diameter of circumscribing circle. So in terms of small letter a, sides of the core, we can represent d. D is equal to root 2 a. And gross iron area, that is a into a. Gross iron area a square is equal to d square by 2. From this equation, we can substitute like this. That is d square by 2 is equal to 0.5 d square. So we have to remember these equations. That is AGI is equal to 0.5 d square for square core. Similarly, net core area, that is AI, is equal to Ki into AGI. And we have already discussed this equation. So AI is equal to Ki into AGI, that is equal to 0.45 d square. These equations can be used for finding the different dimensions such as d and a for the core type transformers. Next is two-stepped or cruciform core. In the case of two-stepped core, we can see that there are two types of laminations. One is having a length that is equal to small letter a. This length is represented by small letter a. That is the width of largest stamping. And there is another stamping which is somewhat which is having a lesser length or lesser width as compared to small letter a. This is the largest stamping and this is the smaller stamping. Then there are two different stampings used for two-stepped core. And here small letter a is equal to 0.85 d and b is the length of smaller stamping. B is equal to 0.252 d. And the relations to be remembered are AGI is equal to 0.62 d square and AI is equal to 0.56 d square, assuming Ki is equal to 0.9. Next is three-stepped core. In three-step core, here also this this is the length of or width of largest stamping. This is the width of largest stamping. There are two other smaller stampings too. So small letter A is equal to 0.9 D. Small letter A, that is width of largest stamping, is equal to 0.9 D, and AGI is equal to 0.67 D square, and AI is equal to 0.6 D square. These are the relations to be remembered for the calculation of dimensions. Next is four-step code. In four-step code, we have four different types of laminations: 1, 2, 3, and 4. The width of largest stamping is A. So letter A is equal to 0.93 D, and AGI, that is gross iron area, is equal to 0.68 D square, and AI, that is net iron area, is equal to 0.63 D square. Now let's see how to choose the maximum flux density in the transformer core. In the case of hot rolled silicon steel laminations, the distribution transformers can have a maximum flux density between 1.1 to 1.35 Weber per meter square. And for power transformers, it can be from 1.25 to 1.45 Weber per meter square. But if we are using cold rolled silicon steel laminations, then the flux density will be equal to 1.5 to 1.7 Weber per meter square. These are the typical values or range of values that can be selected for the maximum flux density. Next, let's see how to choose the window space factor. Window space factor is a factor that represents how the available window area is utilized or occupied by the copper conductors. So it is a ratio of copper area in the window divided by total area of window. There is an empirical formula that can be used to find the window space factor. In most of the questions, the value of window space factor will be directly given, and if it is not given, we have to assume using this equation, and Kw is equal to 10 divided by 30 plus Kv, where Kv is the voltage rating of the high voltage winding for the transformer. But this equation can be applied only for transformers between 50 kVA to 200 kVA. And the typical value of Kw is between 0.15 to 0.45. Next, we will discuss the design of yoke. For transformers using hot rolled silicon steel laminations, the area of yoke, that is AY, is equal to 1.15 to 1.25 times AGI. That is, AGI is the gross iron area of core, transformer core, and AY is the area of cross section of yoke. For cold rolled grain oriented steel laminations, area of yoke is equal to gross iron area, AGI. A rectangular cross section may be assumed for yoke. Thank you.